So in today's lesson, I'm going to derive Euler's equation. To do that, I'm going to consider a cylinder of fluid that's inclined at some angle alpha. The actual shape doesn't really matter too much, but cylinder makes it kind of easy. It's mathematically, so that's what we're going to do. Then in terms of forces acting on my cylinder, you have pressure force. So pressure force is pressure times area. On the bottom, I have P times dA in that direction. On the top, I could have a different pressure, so P plus dP, again times dA, acting down in that direction, and of course gravity acting straight down. I only care about the pressure in this direction because I only care about the motion in that direction. So there technically is pressure in this direction as well, but I don't care about that. I only care about what's going to happen in this direction here. So Newton's second law in this direction, I'm going to call that the L direction, L being positive in upwards at that angle. So in terms of all my forces, I have PdA pushing up, so positive, P plus dP pushing down, that guy's negative, and then Fg going straight down. I only need the L component of that, which is sine alpha. So Fg sine alpha gives me mass times acceleration, Newton's second law. Again, acceleration in that L direction. And then a little bit of geometry, sine alpha based on my triangle, opposite over adjacent, dz over dl. Mass we can relate to density, density times volume. So density, rho, and then my volume of my cylinder is area times length, so A times dl. Similarly, force of gravity, mass times gravity, which can be related to density times volume times gravity. And then volume is A times dl. Density and gravity gives me gamma, specific weight. So plugging all this into Newton's second law, my P, dA, and then I have a minus P dA if I distribute that. So those two guys cancel. I'm left with a minus dP dA. That should be minus Fg sine alpha, so Fg gamma A dl sine alpha dz dl, and then my mass rho A dl times acceleration in the L direction. So now taking that equation we had previously, dividing it by dA and dl, so dA's cancel everywhere, I get minus dP over dl in the first term. Again, dA dl cancels, so I end up with minus gamma dz dl. Then right hand side, dA dl cancels, so rho AL. Then now what I want to do is take the limit as dl goes to 0, so this is a really, really small amount of area or volume for my fluid, and these basically changes become partial derivatives. So I have the partial of P with respect to L minus gamma partial Z, partial L is density times acceleration, where I can pull this partial derivative out front, so I have minus d by dl of P plus gamma Z is rho times acceleration, and that is Euler's equation. One thing worth mentioning about Euler's equation is that if we have zero acceleration, so if the fluid's essentially not moving, right hand side goes to 0, left with the derivative of P plus gamma Z is 0. Integrate that, basically take the derivative, it goes away, right hand side becomes a constant, so P plus gamma Z is a constant. You may have seen that before, go back to lesson 4, that's exactly the definition of the hydrostatic pressure equation. So the nice thing about this is that if the fluid is not moving, it reduces to something we've seen before. So time for an example. I have a piston with 10 centimeters of water sitting on top of the piston, and I want to find the gauge pressure on the top face of the piston. So right here at location 2, top face of my piston. What's the gauge pressure in two scenarios? First scenario, the piston is static, so just sitting there like it is. And second scenario, my piston is accelerating upwards at 100 meters squared per second. Meters per second squared. So for part A, I can start with Euler's equation or hydrostatic pressure. Either way, end up with the same answer. So 0 acceleration, end up with 0 on that side. Integrate from point 1 to 2, so point 1 being the top of the water, point 2 being the top of the piston where I want P2. So P2 plus gamma Z2 is P1 plus gamma Z1. And then P1, top of the water, is atmospheric pressure. Because we want a gauge pressure, that I'm going to call that 0. And then in terms of my Z's, I'm picking Z2 to be 0. So if Z2 is 0, Z1 is 10 centimeters or 0.1 meters. Then it's a matter of plugging these into this equation. So gamma Z2 is gone, P1 is gone. I'm left with P2 is gamma Z1. For water, 9,810 newtons per cubic meter. Z1 0.1 meters. Get 981 newtons per square meter or pascals. So for part 2, now we have an acceleration. So this right-hand side is no longer 0. Another thing we want to note is that in general, L can be any direction because of the way I set up the equation. L is that whatever the angle that is. In this case, it goes straight up and down. So in this case, L is equal to Z. So basically what I can do is replace this L by a Z. And then what I have, basically this equation is just d by dz. P plus gamma Z is negative rho times AL. And then what I want to do is integrate with respect to Z to get rid of this derivative. So integrate with respect to Z. Integrate this side with respect to Z. And I'm going to do it from point 1 to point 2. So this goes from point 1 to point 2. Same thing on this side, from point 1 to point 2. So what that does, basically kills the derivative. And then whatever's on the inside, I have whatever that is at point 2 minus whatever that is at point 1. So left-hand side, I have P2 plus gamma Z2 minus P1 plus gamma Z1. Right-hand side, density, acceleration, both constants. So when I integrate, I just integrate Z and get Z2 minus Z1. And then using the same values we had before, other than now acceleration is no longer 0, it's now 100. Plugging all this into this equation up here. So Z2 goes away, P1 goes away. I can move this gamma Z1 to the other side, now positive. And then I have minus rho AL. Z2's gone, the minus Z1, so that ends up being positive. So I can pull up the Z1 and have gamma plus rho AL times Z1 as my pressure, P2. Then just plug in the numbers. So gamma, 9,810, density of 1,000, acceleration 100, Z1 0.1 meters, gives me 10,980 pascals in that case.